Now we know what the central limit theorem is, and we understand what it says, so we want to use the central limit theorem now. Remember, one of the themes of this course is how do we make decisions using data? And so we're going to use the central limit theorem to tell us how likely it is that something occurs. And that's how we're going to use the data to help us make decisions. And I want to step you through two problems. And in the process of doing these problems, we're going to set up a little Excel template. So that way you can do the problems, for any question, you'll already have everything set up. So for problem one, we're told that we have a sample of 100 randomly chosen adults, and we measure the IQ from each. And we know that IQ has a normal distribution. It's a standardized test. And, it's pretty common knowledge that the mean is 100 and the standard deviation is around 15. And we want to know if we took the average IQ of these 100 people, what would be the distribution for the sample means that we could get? And so we want to use a central limit theorem to get the sampling distribution here. Now, you should stop and ask yourself if all of the conditions are satisfied, and sure enough, we have a sample size of at least 30. We have a random sample, and it's not too large. So we're okay. So now we can use the central limit theorem. So the central limit theorem tells us that the sample means are going to have a normal distribution. They're going to be centered at the population mean, and the standard deviation is going to be the standard deviation of the variable, which here is 15, divided by the square root of the sample size. And so when we work this out, we find that the sample means have a normal distribution with a mean of 100 and a standard deviation of 1.5. So let's go ahead and sketch out what this looks like. So our mean is 100, and I'm going to step out in units of standard deviation. Remember, this is mu hat. So I'm going to have 1, 2, 3 standard deviations on this side, 1, 2, 3 on this side, and if I just add standard deviations and I subtract them, I get this. So this is the distribution of the sample means. In other words, if we took 100 people and averaged their IQ, this is the distribution that the sample averages would have. Okay? Now, Richard Feynman, who was a Nobel Prize winning physicist, had an IQ of 125. And we want to know how likely is it that a randomly chosen person would have an IQ that was better than Feynman's. Okay, first of all, let's think about what's going on, okay? So we're just looking purely at IQ here, right? We're not looking at any sample averages. So we're using this distribution because we're only looking at a single person, right? So this is 100, and this is 115, 130, 145, 85, 70, and 55. And Feynman's IQ was 125, so he's about here. And so how likely a person would have an IQ higher than Feynman's is the same as asking what percentile is Feynman in? What upper percentile is he in? And this is the percentage of people that are going to have IQs higher than Feynman. And so if I were to compute this in Excel, right, I'm going to say it's going to be equal to 1 minus norm.dist. Because remember, norm.dist is going to give me the area always in the lower tail, right? So to get the area in the upper tail, I have to subtract 1 from it. So norm.dist gives me the lower tail. I subtract 1 to get the upper tail. And then I'm going to enter the value, 100. I got to be careful. It's 15, not 1.5, right? And then true. So let's go ahead and enter this in Excel. And we can kind of guess what this is going to be with the empirical rule. We know it's going to be between 84% and 97.5, but that's kind of broad. So let's actually use Excel to do this computation. Okay. And so I'm going to say equals to 1 minus norm.dist. The value is 125, the data value. The mean for the normal distribution is 100. The standard deviation is 15. And we always hit true. And I like multiplying it by 100. I like representing the final result as a percentage. And it ends up being roughly the upper 5th percentile. So there's a 4 roughly 8% chance that a person could have an IQ higher than Feynman's. Now let's switch gears and let's ask the question, how likely is it that the average IQ of 100 people will be greater than Feynman's? Okay, now we have to be a little careful because notice that we're asking what is the probability that an average IQ will be greater than 125. So we're up here in this distribution. Okay? So here the mean is the same, but the standard deviation is 1.5. Notice that the answer is going to be incredibly small. This 3 standard deviation window only goes out 4.5. So if I want to compute this value, I'm going to use this distribution with this mean and this standard deviation. And what we're going to find is that the answer is going to basically be 0 because the answer is so small. So this is the data value that I want the percentile of. The mean is 100. But remember, the standard deviation, these sample averages come from this distribution, right? True. And when we do this in Excel, we're going to see the number is incredibly small, and it's going to basically be 0. So I'm going to go back up here, and all I'm going to do is I'm going to change 15 to 1.5, and you'll see what I mean. It's not actually 0, but it's so small that it's practically 0. And in fact, if I format the cell so that I use scientific notation, if I go down here, well, even with scientific notation, it's so small that it's practically 0. Okay, so the answer is essentially 0. It's so small. For all practical purposes, it's actually 0. Okay, let's change gears now and look at a problem involving a categorical variable. So here I want to suppose that the true percentage of all registered voters who would vote for Trump in the 2020 presidential election is 46.1%. That, by the way, was the percentage of the popular vote he won in 2016. So if I have a random sample of 100 registered voters, what would the distribution for the percentage of people who say they would vote for Trump be? So in other words, I'm looking at the sample percentage, right? And I want to know, what is this? And I know already from the central limit theorem, and you should take your time and make sure that all of the assumptions are satisfied, but they are. Okay, this is going to be a normal distribution. Notice that here pi is assumed to be 46.1, right? I'm assuming this is a true population percentage. So pi is equal to 0.461. And so if I enter this, it's going to be, let me write this down here actually. So pi hat will have a normal distribution. It'll be centered at 0.461, and its standard deviation will be pi times 1 minus pi divided by the sample size, and we have to take the square root of the whole thing. And when we do this calculation, okay, you can do this in Excel or you can do this on a calculator because it's pretty simple. I'm just going to do it in a calculator really quick. You find that it's roughly 0.05. So this tells us that the sample percentages we would expect to see or if we wanted to write this just in terms of percentages, right? Pi hat would have a normal distribution. It would be centered at 46.1%, and the standard deviation would be 5%. And so this is just another normal distribution, right? There's nothing magical about it. We know how to deal with this. We did calculations way back in chapter 7 with normal distributions. So if we sketch this out, this is my 46.1. I step out units of 3 standard deviations, right? So it's 5%, so this is 51.1, 56.1, 61.1, 41.1, 36.1, 31.1. So these are sample percentages. So if you took random samples of size 100 from a population where the true population percentage of people that would vote for Trump is 46.1%, the sample percentages would have this distribution right here. Okay? So how likely is it that we got a sample where more than 50% of the people said they would vote for Trump? Well, we want the probability that the sample percentage is greater than 50%, right? So here's 50%. And the probability that I get a value greater than 50% is the area in the upper tail. So I can compute this using Excel, right? So the probability that we get a sample percentage greater than 50% is equal to the upper percentile, or the area in the upper tail, of 50%. And again, I can get that using norm.dist, right? So this is equal to 1 minus norm.dist. So the value whose percentile I want is 50%. The mean of the normal distribution we know is 46.1. And I'm just going to put in 0.05. It's really 0.0498, but I'm just going to put in 5% here, and then true. And we see it's going to be pretty substantial. You know, it'll be more than 2.5%. So let's go ahead and do this on Excel. And basically I can come right back up to here and just change a few things, right? So here I'm looking at, so this is 50. This is 46.1 for my mean, right? And this is 5%. And I need to take it out of scientific notation. Let me go back to numbers. There we go. And we see it's roughly about 21.8%. So if we look at the area in this tail, this upper tail here, okay. Let's see if I can put everything on one screen easily. So the area in this upper tail is roughly 21.8%, and that's our final answer. So there's roughly a 22% chance that he could get the majority of the vote, even if the true population percentage was less than 46.1. But the primary reason why that's possible is because the sample size is really small, right? As the sample size gets larger, what happens, right? The estimates become much more precise. Okay? So something to think about when you're doing these calculations is to think about how to set up an Excel table that will help you do this. And so before you watch video 4, think about how you would set up an Excel table. What information do you need and how should you set that up? And then in problem 4, in video 4, we'll actually use this sheet to solve some problems. And you can modify your sheet to look like mine, or if you find a way that you like best, you can keep yours.